All right, I'm going to talk a little bit about acids and bases today. Now, acids and bases are important because enzymes enzymes do the work with DNA. All right, and then enzymes, the function so the 3D shape of an enzyme in biology, especially. So let me move that. Okay. So in biology, this 3D shape changes with changes in pH. Right, so I can either turn enzymes on or turn them off by changing pH. So maintaining pH and understanding acids and bases are important in what we do. So there are a couple different definitions for acids and bases, and you don't really need to memorize them, right? You just have to understand them. So hydrogen ions, so hydrogen ions form acids when releasing water. I lost what I was going to say there. All right, so your clue to figuring out if something's an acid or a base, right, is look at the formula that's presented to you. If it leads with an H, it's most likely an acid. Right? And if it leads with, or if it ends with an OH, because OH forms a base when released or is formed in solution. So these things ending in OH tend to be bases. Right. All right, so Bronsted-Lowry was a different definition. It says real similar stuff, right? An acid's a proton donor. Right? So a proton, again, is a hydrogen ion. And a base is a proton acceptor. Right? So if we have hydrochloric acid plus water forms hydronium plus chloride, right, in aqueous solution. Right, so we talk about conjugate acids and bases, right? So this is a strong acid. And this is its weak conjugate base. So water here, right? So in college, we'll write water like this. Right? So you'll see that it leads with an H, so it can be an acid. And it ends with an OH, so it can be a base. So it's what we call amphoteric. It's either. But in this, because it's with acid, right? So this is a weak base. And this is a strong conjugate acid. Right? So every acid is tied to a conjugate base, and every base is tied to a conjugate acid. Right? If it's weak, it's strong. If it's strong, it becomes weak. All right, so that's the basic of this statement right over here. Okay? You won't have to memorize the strong acids and weak bases. That's not important to what we do. So Lewis acid is a little different. And the reason why I bring Lewis acids up, right? So a Lewis acid base. A base is an electron paired donor, right? Because it can accept a hydrogen. So amines, right? An amine is a side group, and it has an extra pair of electrons, right? And we use amines often in science. They make kind of weak bases that accept really well, or even strong bases. So ammonia is a relatively strong base, right? And its formula is NH3. Remember, it has an extra pair of electrons. So for ammonia, this right here would be an H. Right? So what that says is if I have a reaction now where I have HCl plus NH3, right? I get Cl minus plus NH4. Right, plus NH4. And what happened was that hydrogen ion, right, would attach those extra electrons there. So again, this is a strong acid, this is a weak base, and this is a strong base. So this would be a weak acid, right? So NH4 will have a plus here, right? So that's a Lewis definition. All right, so water self-ionizes, as we talked about. So the big thing about water is it's amphoteric, right? So it'll become whatever it's with, right? So water, since the amounts of hydronium and hydroxide are the same, water is a pH of 7, so pure water. So pure water has a pH of 7, which brings us down to the ion product. Okay, so the ion product is just what it forms. All right, so the way we evaluate pH, so pH is equal to negative log of a hydronium ion. Right? Often you see it, instead of hydronium, they put hydrogen. And it doesn't matter, because if hydrogen's in solution, it'll bond with water and make hydronium. And so it doesn't matter which one. So the ion product is just the product. So if I have the dissociation of water, so I have 2H2O, and it forms hydronium plus hydroxide. The ion product, which is Kw, is equal to the concentration of H3O times the concentration of OH. Right, so the important thing here, let me see, is the ion product is always equal to 14. Right? Because Kw would be 1 times 10 to the negative 7, and hydroxide would be 1 times 10 to the negative 7, which is equal to 1 times 10 to the negative 14. Right. So if I typed this number in to my pH problem, right, I'll get 7. Right, because pH, or a log, is a rationalization of the exponent. So what I'm saying is that the log of negative 7 is negative 7, but since I have a negative out front, it makes it positive. Okay, so that's why pure water has a pH of 7. So the pH scale we've all known. We've talked about it over and over again. Right? It goes from 1 to 14, or 0 to 14. 0 to 14. Right, so 0, strongest acid. The concentration of H3O is 1 times 10 to the 0, right, or 1. So the weakest base so this is your weakest acid. So in here the H3O, the 1 times 10 to the negative 14. Right, and that's that ion product. So that's the most amount of ions that water can hold. Right, so 1 times 10 to the negative 14. Alright, so, but if I said POH, but if I use POH, right, so that'd be POH, would be similar to pH, would be the negative log of a hydroxide ion. Right, so POH, 0 to 14. Right. So this is the strongest base. And this would be the weakest base. Strongest base, weakest base. Alright, so you'll notice that whether it's pH or POH defines what it is. Alright. So POH, so we can come there and say now that pH plus POH is equal to 14. That's our ion product, remember? Alright. Oops. If you move these things, I don't want to move them. Alright, so let's move this around. So what we're saying with all of this, right, since these are opposite, right, so strongest acid, weakest base. So if I have my POH scale up here, right, it would go like this. Right. It would be superimposed backwards. So if this is my weakest acid, at that time I have my strongest base. Right? And I would have a concentration of 1 times 10 to the 0. And this would, over here, would be my strongest base. Oh, I'm sorry. My weakest base. Which have 1 times negative 14. Right, so if I looked at, oh boy, what happened here? 1 times 0. That all got split apart. I don't know why. Let me fix that. Right. So what that means, so if I was going to take over here and take this value and this value, right, and I would put them over, so at pH equal to 0, right, we have H3O times my OH 1 times 10 to the 0 times 1 times 10 to the negative 14 which is equal to 1 times 10 to the negative 14. Alright, so that's my ion product. So that's how that works. Got that all mixed up. So that's our pH scale, right? It goes from 0 to 14. So just so that 0, I have my strongest acid, my weakest base. At 14, I have my strongest base, my weakest acid. Now, our body so our blood in our body, our pH is around 7.4. Right? So we'll find that a lot of solutions that we use have a pH equal to 7 to 9. And I can change the pH by adding acids and bases. Right? The only reason I put this here, just know that strong acids and bases are based on the amount of ions they form in solution. So if they release all their hydrogen, right? So if I take HCl, which is a strong acid, it releases all of its hydrogen ions in solution. Right? It doesn't hold any of them back. Right? So that's what we say. So if I look at the dissociation constant, or the equilibrium constant, right? So an acid will form more ions than leave, so it'll be greater than 1. Right? It's have more product. So weak acids will be less than 1. Right? Then we can neutralize strong acids and strong bases. Will neutralize each other. And I can adjust it by using weak acids and strong acids. Right? So if I want a pH that's a little greater than 7, right, I can use a weak acid and a strong base, and then I can buffer it. Right? So this is the important part. Right? So since we are 7.4, right, we want to maintain a pH slightly above 7. Right? So I can use a weak acid and a strong base, right? And I'll get some sort of salt and a pH greater than 7. All right. And we'll use titration, right? So the only reason why this is important is buffers. So we use buffers. So for all solutions, for buffer. And what a buffer is this. Right? They're able to absorb and release hydrogen ions, right, to keep pH constant. So TAE, right? So this is tris. Is a common buffer we use for doing gel electrophoresis for analyzing DNA. So tris is an amine. So it's a relatively strong base. Acetic acid so say Ca2. Right, so that's our formula there. Acetic acid, and this is a weak acid. Right, and EDTA is what they call a chelating agent. And what it does is it stabilizes DNA. So if I look at what we said above, right, so if I have a relatively strong base and a weak acid, I get a pH above 7. Right, so TAE is usually buffered. around 8. It has a range from 7.1 to 9.1. So that's the buffering range, right, for this. So what this does is it keeps my enzymes relatively intact, right, and doesn't allow them to denature, right. So acid-base hydration, right, and that's what we'll do, right. So the equivalence point, so this tris is buffered with my pH of 8, so or with my acetic acid until my pH point is around 8. Right? So that's my equivalence point. And once I get to that equivalence point, the buffer will try to maintain that equivalence point. Alright, so acids that we see or we use binary acids. Right? It's just hydrogen and one other ion. We'll tend to use oxy acids. Right? They end in -ose. We'll use carboxylic acids, right? They have a carboxyl group. And then bases, we'll use amines a lot, right? And then we'll use anions. We use anions quite a bit as well. So there are a bunch of different things. Just a review of pH. And I'll talk today, in lecture about how to solve pH problems. And I'll talk to you soon.